Hello. In this lesson, we look at selection sort, one of the simplest possible algorithms for sorting a set of data elements or numbers. Sorting, as you might already know, is the problem of arranging the given numbers or data elements in proper order, let's say in increasing order. Selection sort is a brute force algorithm. The idea behind selection sort is rather simple. It is perhaps the simplest algorithm for doing sorting. The idea behind selection sort is find the smallest number and put it in its right place. And if we keep doing this until all the elements are sorted, in the end each number will be in its proper place. So we take the elements which are not yet sorted, find the minimum of them, the smallest of them, and put it in its correct place. So after the first step, the first element will be in the correct place. After I steps, the first I elements will be in their proper places, and at the end all the data elements or all the numbers will be in their proper place. Before we actually write the algorithm, that is before we figure out how selection sort actually works, let's look at an animation. Let's try to visually see how selection sort works. In this simple animation, you will see an array, and the elements of the array which are already sorted are highlighted in yellow background. The elements which are yet to be sorted are in white background. As you can see, the elements are getting sorted from the top of the array towards the bottom, right? So here, this is the order in which the elements are getting sorted. So first it finds the smallest number, which is 0, and puts it in the first place at the top of the array. Then it found the next smallest number, which was 1, and put it in the second place, and so on. Now the double arrow that you see shows what we call swapping. Once it finds the minimum, to put it in its proper place, it exchanges that number with the correct location, and that exchanging two numbers is called swapping. So first 0 was swapped into its correct place, then 1 was swapped, and so on, and this keeps happening. Now as it progresses, you will see that at the end the last number to get sorted is the highest number, which happens to be 9. So selection sort sorts from the beginning towards the end. In this case, imagine the same horizontal lines as vertical lines, but the lines themselves have not been drawn. Only the tips of the lines have been shown. So each dot in this two-dimensional space represents a number. The value of the number is its y coordinate, and the x coordinate is merely the position in the array of that particular data element. So again, what is happening is the smallest number, which is the dot with the smallest y coordinate, is selected, and it is shifted to the left of the screen. So the numbers in the bottom left part of the screen are sorted, and the numbers towards the top right of the screen are yet to be sorted. So as selection sort progresses, more and more dots are falling in place, in the sorted order, and the last point to be sorted is the one with the highest y coordinate. Now we are ready to actually try and understand how to write the algorithm for selection sort. So we are given an array of elements A of n elements from 0 to n minus 1, and stated in plain English, selection sort is nothing but from beginning to end find the minimum and put the minimum in its proper place. But that is not quite an algorithm, because it is not pseudocode, it is not yet precise. So let's add more detail to it to make it an algorithm. Selection sort, it takes an array A from 0 to n minus 1. For I equals 0 to I equals n minus 2 do, that is, go through a loop. In each loop we are going to put the ith element in its proper place, right? Find the minimum. How do we find the minimum? We assume that we already know the minimum. Min is I. Then we look at all the remaining elements that are yet to be sorted, right? So from j equals I plus 1 to n minus 1, what we do is, if we find a smaller element aj, which is less than a minimum, we remember that min equals j. So if you find any aj which is less than the current a min, then change min to j. Remember that that is the smallest element. So at the end of this loop, what do we find? We find the smallest element. And where will that smallest element be? That will be in the position min. So all we have to do is exchange ai and a min. That is, swap ai with a min, so that the smallest number a min will come to its correct position, which is I. So this is the algorithm. The inner loop finds the minimum and the outer loop goes through it n-1 times, each time finding a minimum and putting in its proper place. Let's take a simple example and see how this works. Let's say the numbers to be sorted are 43, 9, 26, 4, and let's say 15. These are the 5 numbers to be sorted. So we are going to start at I equals 0, right? At 43. I assume that 43 is the minimum. You might think that is silly, but this is a brute force algorithm. Okay? It assumes that 43 is the minimum. Then it compares the remaining numbers, like it looks at 9 through 15. Is any of them smaller than 43? And each time it keeps remembering that 9 is smaller, so min value will now point to 9. Right? 26 is not smaller. 4 is smaller than 9, so it will actually find 4 to be the smallest number. At this point, it has to swap. This min will be pointing here to 4, and I is pointing here to 43. These two have to be swapped. That is, you need to exchange these two. Right? So the new array will be 4, 9, 26, 43, 15. So what has happened is the smallest number 4 has been found and it has been put in its proper place. Now we have to sort the remaining elements. Right? So I will become 1. That means we are going to start at 9 this time. We assume that that is the smallest number and we look at all the other numbers. In this case, it turns out that no other number is smaller than 9. So 9 itself is the smallest number, which means both I and min will be pointing to 9 in this case. But what do? We still go ahead and swap. That means we are going to exchange 9 with itself, which will not change anything. Right? So the array will continue to be 4, 9, 26, 43, and 15. So in this case, 4 and 9 are already in sorted order. We still have to sort the remaining 3 elements. So what do we do now? We assume that 46 is the smallest element. That is, we are in this loop where I is equal to 2 at that point. Right? Now we look at the remaining elements, 43 and 15. 43 is not smaller than 26, but 15 is smaller than 26. So the min is actually 15 this time. So we need to swap or exchange 15 and 26. So the new array will be 4, 9, 15, 43, and 26. So now the first 3 elements are sorted. After 3 loops, the first 3 elements are sorted. 43 and 26 are actually still out of order, not in proper order. So we start at I equals 3. So we start at 43. We try to find the minimum among the remaining elements. There's only one element that happens to be smaller. So now we exchange these two guys. So the next step will result in 4, 9, 15, 26, and 43, and the entire array is sorted. So this is how selection sort works. Right? So now let's look at how long does it take for selection sort to sort an array of elements. What is the time complexity of selection sort? One of the questions we may ask is, how many times do we swap? If swap is an operation that we are counting, how many times do we swap? You will notice that after each swap operation, each exchange operation, one of the data elements comes to its correct position. It will never move out of that position again. So at the end, we will have done the swap exactly n-1 times. Right? Because you don't need to swap the last element. So the n-1 swaps will put all of the elements in their sorted order. How many times do we find the minimum? Right? For each swap, we find the minimum once. So that is also done n-1 times. But is there some other operation which might take longer than this? How long does it take to find the minimum? This keeps changing because the number of elements we look at or the number of comparisons we do to find the minimum keeps on changing. In the first iteration, first loop, it takes n minus 1 times. Next time it takes n minus 2. Next time n minus 3, and so on, until at the end it takes just one step to find the minimum. Now this sum appears to be greater than those, right? There are many more terms here than n minus 1. So we need to compute this to find the time complexity. In other words, the number of swaps and the number of calls to find the minimum are going to be much smaller than the total number of comparisons done in finding the minimum. So let's actually compute that. The time complexity of selection sort is therefore n minus 1 plus n minus 2 plus n minus 3 and so on plus 1, right? So this happens to be nothing but n into n minus 1 by 2. From your series expansions in mathematics, you know how to do this. So the time complexity of selection sort for sorting n elements is n into n minus 1 by 2. This we say is of the order of O(n) squared, because this is the other terms can be ignored. And if you add the time for swapping and so on, it will only add a term which is of order n. If you add n minus 1 to this, we say it won't make a big difference. So this time complexity is O(n) squared. Actually, the time complexity of selection sort is theta n squared, because it always takes the same number of time or same number of steps, no matter what is the nature of the order of given input elements. So in the best case, worst case, average case, it always takes time n squared. So we say selection sort is theta n squared. That is the time complexity of selection sort. So here is a question for you. What happens if the array is already sorted? Does it get sorted in reverse order? Does it get unsorted first, somehow messed up, and then does it get sorted again? Or no swapping happens at all? Or none of the above, right? Well, the correct answer is no swapping happens. Or in other words, each element is swapped with itself, which is really not necessary, right? So no swapping happens, because each time you find the minimum, it turns out that the minimum is already in its final correct position, so there is no need to swap any elements. So this is how selection sort works. Thank you.